All right, we are live. So the floor is yours, Ashwin.
Yes, you can hear me, right?
Yes, I can hear you.
Okay. Oh, is this visible?
It is, but it is showing up in presenter mode for us.
Yeah, it's showing the same for me too. So,
Maybe it's in display settings at the top.
I'm not sure why that is happening.
Yeah, on the top you see there is a display settings. Swag. Yeah, that's the one.
Okay. So, I start now.
Yes.
Okay. Okay. Hello, everyone. So, today I'll be explaining some of the progress I have made on my research on system identification of the MMG maneuvering model using support vector regression. So I'll be adding on to my talk on my previous presentation. I'll first present a recap of my previous work. Then I will present some of the progress made. So we'll start with the recap. The goal of my research is to predict hydrodynamic derivatives of the MMG maneuvering model given by this equations of motion. So data from tests such as the turning circle test and the zigzag test are used to set up a regression problem to get back the hydrodynamic coefficients. The hydrodynamic coefficients are both linear and nonlinear and are housed in these XH, YH, and NH parts of the forces. And when expanded out, you can see how they're expanded out here. And we have 5 hydrodynamic coefficients for the surge and 6 for yaw and the yaw and sway, the sway and the yaw respectively. And you can see that they're parameterized by U, beta, and R, where beta is the drift angle defined by tan inverse of minus V by U, where V is the sway velocity and U is the surge velocity. So, and the predictions are to be made using support vector regression. So let us look at how the equations of motion are restructured for support vector regression. When I try to expand out the equations of motion by putting in the values of the hydrodynamic coefficients, it looks like so. And my goal is to separate out the hydrodynamic coefficients and put everything else to one side. So I define these 6 matrices x, y, n, a, b, c, and rewrite the equations of motion in this form to form a regression equation. You will notice that this regression equation is of the form ax equal to some constant, where here a is these factors to be multiplied with the hydrodynamic coefficients. So ax transpose will give me this right hand side, and from the maneuvering test for turning test and the zigzag test, I can construct A, B, C matrices and the corresponding right hand side matrices. And my goal is to find X, Y, and N matrices. This is to be done using support vector regression. I will feed in values that I get from the test and construct these matrices, then regress out X, Y, N vectors. And X, Y, N vectors will contain the hydrodynamic coefficients. So this was my last result, the old regressive derivatives. As you can see, the linear derivatives, YB, YR, NB, NR are mostly accurate, and some of the surge derivatives are also accurate. But the majority of the non-linear derivatives, YBB, YBR, beta, beta R, beta RR, where they are mixed, are not matching exactly. And this was attributed to something called parametric drift. And parametric drift mainly occurs when during regression of nonlinear coefficients. But they don't affect the linear coefficients that much, but the nonlinear coefficients are affected due to parametric drift. So what is parametric drift? Parametric drift occurs due to the nonlinear nature because of linear dependencies in the training data. So when I construct these ABC matrices, as you can see, I will have a big column of this for each time instant. If I were to sample my maneuver for, let's say, 100 seconds at 1 second each, I would have a big vector matrix of containing u square, b square, beta r. So in the rows and in the columns, I will have 100 points, data points. Now the problem occurs when some of these columns, let's say beta square and beta r, are linearly dependent on each other. Let's say if beta square and beta are linearly dependent, the regressor won't actually know how much weight to give to beta square factor or beta r factor. Thus, even though the end result, if I were to plot the trajectory of the regress derivative, they would be the same, but the actual coefficients may vary. So that is what is happening and is why is causing this error here. So the regressor does not actually know how much weight to give to beta, beta, beta or beta, beta r because of this parametric drift occurring due to the linear dependencies. So that is the main problem that I'm facing. And the solution to this that I have implemented last time was one, addition of Gaussian noise. By adding Gaussian noise, I can cause these parameters to be excited and cause much more variation, thus alleviating a little bit of the linear dependencies in these columns. And one another technique is called batch learning, wherein I take two maneuvers and add the two maneuvers together. So A1 will correspond to my turning circle maneuver, A2 will correspond to my zigzag maneuver. So I can restructure the equation, so the regression equation like this, and correspondingly modify the right hand side also. So this also has worked, but this hasn't given exact results either. So something new that I have tried this time is to add one more maneuver in, which is the spiral maneuver. Now in the spiral maneuver, the resulting trajectory looks like this. I start the ship at 0 with some velocity, then I go from minus 35 degrees to plus 35 degrees in increments of plus 5 degrees, and I increment to plus 5 when the yaw rate becomes constant. So if you were to look at the rudder, you can see it starts at minus 35 degrees, and when the rate becomes constant, I just decrease it by 5 to minus 30, then minus 25, all the way to plus 35, and the resulting figure looks like this. Now what this maneuver adds is more, it gives more data to the regressor so that it can identify the coefficients better. And there is some, the beta, u, v and parameters are varying very much here too. So this also helps with the regression and can aid in identifying the coefficients better, these coefficients. So these are just by adding that one maneuver. And I also added one more thing called hyperparameter tuning, wherein I cycle over a large values of C and epsilon so I can find optimal values. So these are the results found by the hyperparameter tuning for each of the search sway and search sway and your directions. So these are the results of the regress derivatives. You can see that for the search, most of them are like these are under 10%. While x beta beta are not matching perfectly. You can see the error percentage here. For the linear terms, you can see the linear term here. It's less than 5% error, less than 10% here too. But for the sway and surge, you can see only the linear terms y beta, yr, n beta, and nr have less than 5% error. The other nonlinear terms still have a high amount of error here and here. So this was where I was getting stuck. So I tried some other stuff, and you can see the reason why the nonlinear terms are. You can see how they are linearly dependent by checking the correlations between these variables: beta cube, beta square r, beta r square, etc. And this can be done by plotting the correlation matrix. So if you were to look at the search correlation matrix, you can see that the terms are not that correlated, especially the u square, they're negatively correlated here. But if you were to look at the sway and yaw, which has beta cube, beta square, and beta r square, if you were to look at this part, you can see that the correlation coefficient is almost 1, which means that they are really highly correlated. So beta cube and beta square have a correlation of 1. So essentially the regressor has no clue how much weightage to give to beta cube or beta square r. So it randomly assigns the total value of some bit to this one and this one. So that's why the regress derivatives are erroneous. So this is mainly found in the beta terms. You can see beta r square terms also have a really high correlation factor of 1, while the others don't have that much. So as close as the correlation factor becomes closer to 1, the more linearly dependent these columns will be. So this is the explanation for why parametric drift is occurring. So this is another way of we tried to reduce the parametric drift. What I did was I knew that I know that the linear terms have very low error. So what I'm looking to do is taking these terms out of the regression equation. I will take I will only regress the beta terms since I know that the beta terms are erroneous. So these are the derivatives that I'm looking to figure out now, and these are my modified equations. From the modified equations, I was able to effectively get out beta x beta beta, wherein the x beta beta term here had around 60% error. By doing this isolation, I was able to reduce it to just 2% error for x beta beta, and for x beta r about 1%. X beta, the beta power 4 term still has a higher, but it didn't work for sway and yaw here. Sway and yaw still has a very high amount of error, as you can see here. And this is mainly due to this correlation factor being 1 followed here. Yeah, so that's it. That's where I am right now. Any questions?
All right, any questions?
Ashwin, can you explain again how that your spiral maneuver reduced the error? I didn't get that.
What? Like initially I just started minus 35 degree. Then it just goes forward and it spins, right? It turns. It once it achieves a constant turning rate, I will
What is
reduce
exactly
it.
happening here? How is your prediction error reducing here?
What is happening is that I have more data. Essentially, that's it.
Oh, that's it.
And yeah, so this beta cube, this will have more variation. If this variables have more variation, the dependency becomes lesser, and thus I'm able to, yeah.
Okay.
So, anything else?
I have this doubt that can you go one slide back? So this ABC are the things that you have measured, right? The data that you have
Yeah,
is
yeah,
ABC.
yeah. If I have a maneuver, I will take one time instant t equal to 1, calculate u square, b square, beta square, and for like some 100, 200 points, I will calculate. This is my training data.
Okay. So this is known, and what else? If you are doing some regressing, so maybe like fitting a line, say, then what is happening is that you have x and also y measured at that value.
Yeah.
So this y, what is that y exactly in this case?
Y here is my right hand side here. X is this A, B, C. Basically, if you are talking about like the Python terms where you have some give X and Y, that this will be my X and this will be my Y.
No, I'm saying this like
No, I think what he's asking is where do I get the right hand side terms? Am I right, Balu? Is that what
These are also calculated from my data. You can see the accelerations. Accelerations are calculated by Euler integrations. These U dots. There are some other terms too here, which I have not written. They are calculated using delta, which I also measure at time.
So like say these three equations, we put these at any instant. I put the values of u beta, u square, beta square, all of those values that I have measured in these
Yes.
three sets of equations. So that will give one set of capital X, capital Y, capital N, right? Say
Yeah,
capital
yeah.
X, one set of capital X,
Yeah,
capital Y,
yeah.
capital
So
N satisfies those.
what the SVR does is it tries to optimize X, Y, N so that all of the data fits.
Yeah. So if their data is bigger than the uh, number of unknowns, so what exactly is it doing then? Like,
Yeah, yeah.
like
This
an
is an
example.
optimization algorithm, right? So it optimizes across all the data so that it will find optimal values of X, Y, and N.
No, I think what he's talking about is I think more number of data points than the number of quantities you want versus the other case where the number of data points is less than the number of quantities you want.
Yeah, yeah. But if you have, let's say you have equal number, but uh, that won't be enough, right? You'll get really erroneous solution if it like just if the number of unknowns equal the number of variables here, because the maneuver is large, and the terms inside X, Y, N need to mirror across the big maneuver and not just some data points.
Yeah.
That's why we are using regression.
So in if you just
So it will
after
be like
solving,
if you were to look at some 2D case, suppose you have a very complex sine wave or something, and you were just to sample 1 or 2 points, you can't like some a really low amount of points, you won't be able to fit it perfectly, right? To fit it perfectly, you need a large number of points. It's a regression problem.
yeah. Okay.
That's what I'm trying to do here.
Okay. Any other questions? Any questions by our latest joinee, Anand?
Sir, no, sir.
No? You got everything what he was talking about?
Not, no, sir, not like that. But I'm just new to this, so
That's why this is to break the ice. Don't be so new. Happily ask away.
yes,
Because others have heard it before, so that is why they may not have as many questions. But you definitely will have because you have not seen this before.
yes, sir. So basically, what are we trying to do over here? Like, uh, my guess is we are trying to optimize the something like get an equation using a lot of data. But
Yes.
actually, what are we trying to do?
So I'm just trying to find these coefficients x naught, x beta beta, this coefficient xrr, x
I
beta
don't
beta
think
beta.
I don't think he's asking that, Ashwin. He's talking about what is the motivation behind finding those things. Why do we need them? Like, what is the bigger picture? Is what the question is about.
Is that what your question was? Do you want to know how I'm finding this or why I'm finding this?
No, why are you finding this?
Oh, okay. So I think I'm finding this to model ships better.
Come on, don't be so skinny on words on this. You can expand a little bit more.
Okay. So basically, ship maneuvers. If you want to model ship maneuvers in a mathematical form, you'll have to you can't exactly maneuver ship motions using a mathematical model, a simple mathematical model, uh, because ship motions are very complex and they are highly nonlinear in nature. So if you want to model them mathematically, you will need high amount of coefficients which integrates uh, u, v, and r of the ship motion. So to get these coefficients, what you do is run tests and run model tests in real life and figure this out from the graphs. You calculate the slopes and get these coefficients, and these can be much more expensive because you're using real life model tests. So what we are aiming to do is from a free running small scale model, we are trying to regress out these derivatives, which can be much more cheaper and maybe more accurate because there we allow for other terms to be included as well. Basically, we are trying to model ship maneuvers perfectly or as perfect as we can using high order derivatives.
Yes.
And the problem is finding these high order derivatives.
Yeah, I got it. Thank you.
Okay.
What is mx dash and my dash?
These are the hull hydrodynamic coefficients. So these are the hull forces. So if when a body, a ship is in water, the interaction between the ship hull and the water is described by this.
No. He's asking about mx dot and my prime. Yeah, am I right, Shraddha?
No, he said
Yes, sir.
NH dash, right?
No, mx dash and my dash.
I think it is mx prime and my prime is what he's asking about.
Okay. All of these are primes, okay? These are just atom mass in the acceleration, atom mass in the y direction.
So what they are indicating?
Atom mass, atom mass is the, what do you mean, what they are indicating?
No, what does added mass indicate? I'm also curious, Sachin.
Yeah, I'm also curious.
No, I
Uh,
am curious about your answer, not about his question.
Okay, so atom mass in the x, y, y directions account for the additional mass of water that moves along with the ship in the respective directions.
So it is the mass of the water which oscillates along with the ship. So you
Yes.
can think of it as a what you call. So when you're moving something in the air, okay, you don't have this concept of added mass. But when you're moving something in the water right next to your body will also oscillate. So suppose I move my ship up and down. As I move my ship up, the water tries to take the place which was created. Again, as I move my ship down, the water has to go away from that place in order to make way for the ship. So there is a certain amount of water, you can think of it notionally as a certain amount of water which is oscillating along with the ship. So that mass is also included in your dynamics. And that mass is what is given as the added mass in surge, sway, and yaw. So in yaw, it will not be a mass, but rather will be a mass moment of inertia, which is why you represent it by J in that equation. Did that answer your question?
Yes, sir.
All right. Other questions?
Interesting.
Ashwin,
Yes.
how much percentage increase in error detections when we are introducing the spiral maneuver?
Spiral maneuver, I think it only affected the surge. I was able to regress out these four perfectly, except x
Or
beta
any
beta.
particularly any of the coefficients are reducing due to influence of spiral maneuver?
When I added the spiral maneuvers, I drastically reduced the error. It didn't help with the non-linear terms.
Adding the spiral maneuver, did it improve the percentages on the sway and yaw linear coefficients as well?
No, a little bit, I think, not that much. The linear coefficients are like really accurate, below 5% error.
Yeah, but by adding it, did it change anything or
Didn't
not?
change that much.
Like,
Can
was
you
it a
please
few
show the
percentage points?
Yes.
Go ahead, Krishnavelu.
Yes, Ashwin, can you please show the comparisons of the error reductions in when we are before the spiral maneuver and after the spiral?
I haven't calculated the error reductions here, errors here.
Now we are show the slide and you can explain.
What?
You can show the before data, before hydrodynamic data, and now we are reduction of the error in data, then we can show.
No, what
This
he's
one
saying
is
is
better
just
able to.
the numbers. Let's go back to that previous table, the one prior to of including spiral maneuver. Okay, 0.22803, 0.0376. Okay, let's go there now. 0.03.
It's almost the same.
No, it became better, right?
But it's minuscule.
Yeah, it is. And it became better in
But
YR, but not so much in YB. But it was minuscule. Yes, it was. It didn't change it.
like we are interested in the nonlinear terms right now, right? The linear is pretty much okay for these and these.
No, that is fine. It did not work on the non-linear one. We already know that. Whether it had any effect on the linear was the curiosity.
No,
But it did not. Didn't do much.
it did for the search.
It did for the search. Okay.
Yes.
Other questions?
Yes, sir. You said you have done some hyper tuning in this the program. So can you show us?
I haven't put them in the slide. I'm just cycling over a large number of values for C, epsilon. I have C from 1 to 40 and epsilon from 10 power minus 5 to 10 power minus 16. I have 5 or 6 values. I cycle over the 4 values and check which one is the best.
Okay. So you have done something like grid search.
Yeah, which is basically it's a grid search over some values.
Okay.
Hello.
Yes.
Yeah. So in the can you go to the previous table?
Okay.
This one. So I still didn't understand that how the higher order derivatives are affected. Means why there is some error in that due to parametric drift you told, but I didn't understand that. Why the error is there?
Okay. What happens when parametric drift occurs is you can see this table, right? If you were to look at this beta cube term here, you can see that it's highly correlated to beta square r term. So if you come here, so in this table, beta cube and beta square r are highly correlated. And the coefficients that are pre-multiplied onto beta cube and beta square r are what the regressor tries to identify. So if these what?
Highly correlated means what does it mean? Highly correlated.
It means that these are linear combinations basically. This beta cube can be written as a linear combination of this and this. That means the regressor can't identify between beta cube and beta square. Thus, the coefficients that the regressor will give to these things, like it allows them according to, it allows them randomly, I think, based on the gradient descent optimizer.
Did that answer your question, Aditya?
The regressor is not able to figure out how much to give this, how much weight to give this, or how much weight to give this because they are related.
Okay, Ashwin, can you go to that previous slide where you had the other equations?
Which other equation?
The one where you have the actual coefficients multiplied by these things.
Yeah.
Yes, right here. So Aditya, what he says here is, suppose we take the top term, x beta beta times beta square plus x beta r times beta r. Okay, and it means that you are trying to identify these coefficients x beta beta and x beta r such that the sum is equal to something. Suppose I know that the sum of these two terms is equal to some value, 100, let us say. Okay, now if beta square and beta times r both are highly correlated, which means that if beta is more, if beta square is more, beta times r is also more. If beta square is less, beta times r is also less. So you see a kind of a similar variation. That is what the correlation coefficient is telling you. That as this varies, that also varies in a linear manner. Not linear, it says that it is varying in a directly proportional manner.
Yeah, so these two will be related. So any increase in beta square you will get a direct increase in beta r also.
Yeah.
So both these terms they are related now. The regressor sees them as being related. So if it tries to increase one of these, this will also increase.
Okay.
No, I'm trying to drive home a point. Give me a second, Ashwin here.
Okay.
Okay, so I assume that those two terms add up to 100. Okay,
Yes.
Aditya?
Yes. Yes.
Okay, so if they both add up to 100, then the question is x beta beta 50 and x beta r 50, or is one term 25 and the other term is 75? I can add both of them. 25 plus 75 will also give me 100. 50 plus 50 will also give me 100.
Okay.
Isn't it? So the question
Yes.
is, which one is it? Because they are linearly correlated, I can't make out. But suppose if beta and r were not correlated, let us say, okay, in which case what would happen? In one maneuver, if I got two options, I have either 50 and 50 or 75 and 25, but then I have a separate maneuver in which beta and r are not correlated. That will help me eliminate one option.
Okay.
Because in that other option, when I substitute 25 and 75, I probably will see that the right hand side doesn't come to 100 but comes to 120. Are you able to get my point?
So for other maneuver means another beta square and beta r values.
Correct. So one could be, let us say, zigzag maneuver. The other could be, let's say, turning circle, as Ashwin was talking about.
Okay.
So then that there is a way to kind of get rid of that discrepancy between them and say that, okay, I now know I have a maneuver which will give me the perfectly unique coefficients set, which will now reproduce my original dynamics. But if both beta square and beta times r are highly correlated, then I can't find another maneuver is what is happening. Or I have to find a maneuver where they are not correlated. Then I
Okay.
can be sure to distinguish which one is, how much contribution is due to the first term and how much due to the second term.
Okay.
It's like as if I gave you 100 rupees, but then you actually collected the 100 rupees, let's say from Vallabh and from Ashwin. But I don't know, when you give me a 100 rupee note, I don't know how much came from Vallabh and how much came from Ashwin. So it's
Okay.
that problem. Which one,
Okay.
how much is the contribution? Now, yes, before I have some things to add, any other questions?
Sir, so
I
like,
know.
One
okay.
by one, one by one. Vallabh, you go ahead.
So this we have problem with beta beta terms and beta r terms, right? So a maneuver that like do we know in beforehand what a maneuver uh, has more effect by, say a maneuver is more affected by r, so we can use that one to uh, you use more weightage on that maneuver to give us the x beta r term or something like that.
Yeah, that's right. Suppose if I choose a maneuver in which there is absolutely pure yaw, doesn't have any sway, then I have eliminated the contribution due to x beta beta, right? Then only contribution is due to x beta r. Possibly that contribution also will be zero because beta's contribution is already zero there. But yes, if you can find a maneuver in which these terms are not so linearly correlated, then you are in a better position to identify the what is happening with this thing. Now, the other problem might here be, see, and this is the other thought process which I'm having. We are talking about these maneuvers and we are saying that these terms do not have linearly correlated. But that is possibly also true if the maneuver is linear in nature. Suppose the non-linearities don't actually affect the dynamics in this particular maneuvers that we have considered, then it is hard to argue that beta and r will not be linearly correlated. It's a linear system, so they would be linearly correlated as we studied in our course, right? Whenever we have a turning circle, if we want to make a sharper circle, we need to have a more sway velocity and more turning rate. So they go hand in hand, right?
Sir, can you repeat this again? What you told about linear thing?
Yes. So suppose that we did not, so consider his second equation there, the one with respect to the sway force. Let's say all the other terms are very small. Beta cube is small, beta square times r is very small, beta times r square is small, and r to the power cube is very small. Then the contribution due to the last four terms is really small in the dynamics. If suppose I did not consider them at all, even then I would have been able to predict the maneuver fairly well, isn't it?
Yes, sir.
So now in that case, when it is a linear system, beta and r will be correlated, definitely will be correlated, and therefore it will be hard to argue that they may have actually much significance at all or not. So what I'm trying to give here is a slightly different way of looking at it than how Ashwin is looking at it. Ashwin is saying that these two terms are highly correlated, because of which we are not able to identify. I'm saying they may not be relevant also. They may not have dynamics actually, which is important. That also may be a reason why we are unable to figure them out.
But then you're like going against how the model is described, right?
No, it is just a model, no, Ashwin. There is no necessity that the model
But the
was.
model was established through tests and
No, it was established through hydrodynamic derivatives calculated through different types of tests. It doesn't mean that in all maneuvers all the coefficients will be equally likely. So suppose I had a pure sway maneuver, a pure yaw maneuver. Then for that maneuver to be described, this y beta 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 need not be required actually, because there is no beta going to happen in that particular maneuver.
yes, but that is just for one maneuver. We're trying
No,
to get a
no, not just like that. What I mean is their importance may not be there. Suppose y beta times beta is 10 times larger than y beta 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 times beta cube.
okay.
Then it is very hard to argue that I can get that third order coefficient unless and until I perform a maneuver in which beta is really large, where beta cube is significantly larger than beta, such that the contribution due to this whole term y beta beta times beta cube is more than the contribution due to y beta times beta. If a maneuver can be achieved in such a manner, then I will be able to say I can predict that coefficient more precisely. So it's not
Yes.
just a question of correlation, it's a question of whether they are significant to the dynamics or not also might play a. I'm not saying that correlation doesn't have a role to play, definitely it does, but possibly there might be something more to it also. And as I am thinking in that manner, I'm having a thought process, but I will reserve my thought process for another 5 minutes and give Mansi a chance to ask her question.
Right. I just wanted to understand that how are we like after isolating beta values, how is the regression getting better? I didn't quite follow that part. I think it was a follow-up based on I
Okay.
think the previous question, which I think Vallabh asked.
Okay, you're right. I'm not sure about that. It did get better, but I'm not sure why it got better.
What got better? Sorry, I didn't quite get the question. Mansi, what was exactly the question again?
Yes, sir. So I didn't follow how isolating beta actually made it better. The predictions better.
How taking the linear terms out would possibly try to make it better. Did it
Yes.
make it better, Ashwin? We
It made the search better, not
made
the
this
others.
look better. Okay. Yeah.
I'm not sure why that happened. Like, sir told me last time to try that, so I tried it. It just made the search better.
Oh, come on, don't give that answer. That's no way to do research. I tell you to
Yeah,
jump off into a well, you will jump off into the well. Come
I
on.
tried. I tried doing it, and it worked. Possibly because the terms there became decoupled from the beta.
Yeah, so I think my thought process was this, that suppose y beta times y, so whatever terms which were having larger error, their contribution might have been lower. So suppose now that we know one of those coefficients with a good accuracy, we move it to the right hand side in the regression, on the left hand side for the regression problem, then possibly we may be able to get a better fit, is what was the thought process. Because we already identified it. Did that make much sense, Mansi?
Yes,
So
but it didn't work for the other two though. It only worked for the search.
Correct. It didn't work for the other two for probably a different reason. Because of the high amount of correlation
I
between.
also tried removing some other terms, like beta cube terms, beta square terms, that did not also help.
Then possibly the answer might be that it might not be having significant dynamics in the maneuvers that we are considering. And
Yes, that may be the case.
so
But
this is
but
where
I was trying with like multiple zigzag maneuvers, 25 10, 20
ah,
20,
so as
10
you were
10.
presenting, I had this what you call, I don't know whether it's a brilliant or a what sort of an idea it is, but one idea to do it is you you flip the rudder angle. So instead of doing the spiral test where you were decreasing it in increments of 5, right?
Yes.
Minus 35 to 35. You start at minus 35 and you move to you move to plus 30. From there you move back to
Oh,
minus
okay.
25.
Okay.
So that will do what is that your transient time on the trajectory will increase. It won't
Okay.
settle into a steady state so quickly. It will take longer time to settle because it is turning one way and I'm suddenly asking it to turn the other way, isn't it?
Okay.
And then when I try to do that, that is where I believe, or this is my hunch, okay, where I feel that those extra derivatives which you have, beta square, beta cube, r times beta square, they may start to show an effect because I'm trying to move in one direction, but then suddenly my rudder is trying to do something else, trying to push me in the other direction. I may be able to excite those dynamics into it, is what my thought process was.
Okay.
But then, if you look at the rudder, look at the zigzag maneuver. That is what
Like,
exactly it is. Yeah.
well, what I think is like because beta and r are related so highly,
Hmm.
I think it's going to be very difficult to like separate them out.
Suppose we try a maneuver in which where there is no beta. So
Yeah,
suppose
suppose you say beta is 0, what happens to the equation is all of these terms will be 0. This will be 0, x naught. Then I think the only option is to just like go straight.
no,
There
no,
won't be.
no. I'm talking about a pure yaw maneuver. But then to achieve that pure yaw maneuver, you need a controller. So which means that you have to kind of make sure that your rudder is doing something such that you are achieving a pure yaw. You have to formulate a control law, isn't
Okay.
it? Then if you are able to achieve a pure yaw maneuver, then all these beta terms will be 0, but your XRR, you can estimate that precisely, possibly from it. Or if you're looking at the sway maneuver and sway equation of motion, YRRR might be a
You need beta to be 0, right?
beta will be 0. So therefore, only the terms which will be affecting will be YR times R and YRRR times R cube.
Okay.
Right. So then you may possibly get a better estimate on YRRR in that maneuver.
Okay.
Right. Similarly, if I can do the same unfortunately, you can get away with pure yaw, but you can't do a pure sway. That's
I
not
don't,
possible
yeah, that's not possible.
with a free running model, at least.
Yes.
Right. So at least that we can try pure
Also,
yaw.
pure yo, I don't know. I'm not sure if it's possible just with this control radar.
I think it might be possible.
You need 2 points of contact, right? 2 points of control.
2 points of
Control, like in the test.
no. Here no, between the sway and the yaw, you're keeping beta at 0 and you're only trying to control R. You're not trying to control R, you're only trying to control beta. Yeah, it is an underactuated system because you have only 2 degrees of freedom and one what you call control.
Control.
Yeah, one control input. So it is an underactuated system, but I think pure yaw can be achieved. Like theoretically, it can be achieved, but pure sway cannot be achieved because of the non-holonomic nature of your constraints.
Okay.
Because you can't move sideways with a ship. That's why you can't achieve the pure sway. But pure yaw may be achievable, but we have to check on that.
Okay.
Okay. All right. We will think more about this. That's a good idea. Also, the other aspect is from the pi Cindy, were we able to identify whether any of these dynamics were actually important from the trajectories which we got?
No, I am not was able to do that.
Let us try that, Ashwin, because that will tell us whether we are on a wild goose chase or not. At least we will know for sure, rather than being on the wild goose chase and then realizing, oh, it doesn't work. It's a preventive step which may help us.
Okay.
Because what it is going to do is it is going to look at the pure data and try to come up with a minimalistic sense of coefficients which will be important, right? So that may be one step at least, because it will use a different sort of an optimizer, but the problem is slightly different there.
Okay.
But it's worth a try is what my feeling is. Okay, all right, okay, but this is good work. I mean, I like the idea that we're looking at the different possibilities how we can improve it. Any other maneuvers which we can think of which can possibly make this beta and R less correlated?
I have another question, sir. Will there be any relation between the lower order coefficients and the higher order coefficients?
Relationship between
The lower order coefficients and the higher order coefficients.
relation in terms of?
No, is there some relation between the lower order and the higher order, which we can try to model? So I was thinking like whether, so we currently we are able to predict the lower order coefficients, right?
Correct.
So by any chance, if there is some relation between the lower order and the higher order coefficient, why can't we model that?
I
Will
mean,
there be anything such that
they are related through the geometry of the vessel, definitely, but I don't think
is
that.
it possible to model that?
So you want to say that you want to express, let us say, y beta 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 in terms of y beta and y alpha,
Yeah,
something of that sort.
yes.
I doubt that we can do that because these coefficients are nothing but they are basically a Taylor fit,
Yeah,
right?
correct. Yeah.
So when we fit,
It's just like.
If there is any, it will just be added on to y beta.
Okay.
and you see if there is a relationship, then it really walks into the problem which Ashwin was talking about with parameter. If I
Right.
can express y beta beta in terms of y beta and yr, then I'm saying that essentially what I think is y beta is not y beta but y beta plus something more. And the regressor is simply not able to find out how much contribution is due to that term and how much due to the third order term.
But if there no, I what I was thinking was like, so if we have this y beta yr, say if there is some sort of relation between the other coefficient, so why not we like put like a neural network or something which takes in these lower order coefficients and try to predict the higher order coefficient?
But do you want to do that for one particular ship or for multiple ships?
Yeah.
I mean, the reason for doing that might probably be justified if we are looking over a large number of ship types and to see, identify a generic relationship between them.
Right. Okay.
But here the problem is tied to a very specific ship type,
Okay, sir. Okay.
right? So,
Mm, yeah.
yeah, my only curiosity is, Ashwin, when you go to your slide on that correlation coefficients, yeah, you see this beta cube and beta square r and beta times r square. They are exactly one.
Yeah, the problem is exactly one. I read that if it's exactly one, it will be a problem.
It definitely will be a terrible problem. Even 0.96 and 95 will not be that easy. And that is, if you can see between the surge sway and yaw, that is where the problem lies. Why the surge improved is because of that.
Hmm.
So in all our, so this is purely from the data, right? This is correlation.
Yes, I added up data for multiple manuevers to make this.
Correct.
This is after adding them up. Before adding, it was worse.
Yes. So what it is telling us is that all the maneuvers that we have, these quantities are highly correlated, which is why
Yes.
it is becoming very difficult to predict.
Yeah, and in that other model, it's because it's parameterized by delta, it will be like the correlation matrix will be much better and the condition number will be better.
If the delta is there, if you use an
Yeah.
model.
Yeah, if you use the Apkovitz model, it will be by delta. You won't have this correlation between beta and r.
Why these terms will be there also, no?
Yeah, but it's also parameterized by delta, right? There will be delta terms.
Yeah, there will be delta terms, but these terms will still be there.
Yes, that is true.
And if it is purely from the data, then I should see a 1 there also.
Hmm.
Right? At least within these three terms, I should definitely see a 1 come out. Okay. So this is okay. This is at least one step in the right direction. We know that they are highly correlated. My only concern before heading off more into this direction is to see whether they are significant in the dynamics, which is why I'm asking you to look at that Cindy algorithm to see whether if we are trying to give these as the input points,
Okay.
and you can actually do that also in the Cindy. When you give the modeling, you don't give the rudder modeling also. You kind of include an Apkovitz terms for the rudder as well.
Oh, give it delta also.
Delta also. So we will identify a model which has the minimal representation, simplest representation, but no simpler representation in the Apkovitz terms.
But we have to choose some order, right?
Yeah, choose order 3 or 4.
Okay.
Which means it will take all possible combinations between the 4 variables.
Yes, it will do that, but it'll also have even powers and odd powers.
Yeah,
How will we choose? We are choosing between those two.
We are choosing between?
Are we choosing?
No, don't choose between those two. That Cindy algorithm is supposed to, so it is by default, it's supposed to give you that for beta square, the coefficient will be 0. It is trying to identify the minimalistic sense. So you feed it everything.
Okay. Yeah. Okay.
Okay.
I did try that, but like for a sway and yaw, the even powers also had significant terms.
Were the terms bigger than the ones which we saw in this one?
Like they were of the same order.
So beta square terms are also coming out, which are of the same order as the terms of beta and beta cube.
Yes.
So then that means that we need to include maneuvers which are opposite as well. So if you did a turning circle maneuver one way, you also need to include the turning circle maneuver the other way. Similarly, if you did the zigzag one way,
how will I include that? Will I just add them up?
Yeah, so in your data set, you just add everything up and give it. There should be equal representation for both.
Okay.
Otherwise, what happens? It gets skewed in one direction. That is why it will identify a beta square.
Okay.
And also similarly, when you did the zigzag, if you started with the zigzag with a port starting, then you also do one with starboard starting rudder.
Okay.
So it will give a counter example to it, so that these things can be somewhat eliminated. These are problems which are what you call more in the data domain as we are talking about these. But that is more important. So unless you have a clean data which is unbiased, we will run into issues like this possibly. If beta square is getting identified, then that clearly tells us that we need more maneuvers. We need equal number of maneuvers for the port and the starboard side.
Okay. And how accurate do we need the regress maneuver derivatives to be?
How accurate do you want the?
Coefficients to be?
You are not going to be having control over that in Cindy.
Yeah, and not there, like in general. I wanted to know how accurate they need to be.
Anything under 5%, I'll be very happy. Up to 10% also is okay. Anything more than that is little too off. 5% is engineering accuracy usually, but for the nonlinear terms, maybe even 10% if you can get, we'll be happy. It's not a question of you can get. I'm not trying to see whether Ashwin can get me the numbers under 10%. I'm trying to understand why they won't come under 10%. Okay. It's not so much so that you should get them, so that I should understand why the process is failing. Is the curiosity here, isn't it?
Okay.
All right. Okay. So this is some good way to go about it. Let us also think about that pure yaw maneuver, Ashwin. That will require some more thought process, though.
Like, even if we do the pure yaw maneuver, then how do we proceed?
If you do the pure yaw maneuver and you include it into these ones, into your data set, then you should get your R coefficients improvement, the YRRR, NRRR, those terms should see a jump in the improvement.
Okay, we improve those.
At least
Then?
a step in the right direction, so that we know that those terms have now been identified.
Okay.
Then we can possibly try out again the approach which you were trying previously. We take the known ones and port them to the other side, and then try to identify the other ones. But there also you will still face the same problem probably.
Yeah, that's what I did, right? I put in the values for YRR and YR, but it was still not improving.
Yeah. But at least can we improve the R values is the question. Can that be improved? So for example, you see YRRR, here is 740% error. It's an order of magnitude error, right? Similarly, YNRRR, order of 100% error. So can we, wait a minute, how is that 100% error? That is
I'm calculating with real as a base.
You're calculating with real as the base, okay. Alright. Alright. This value is so small that it has no meaning.
Yeah.
The error comes. Okay, alright. I think so then let's summarize. So what we have thought of is, one thing is to try out the different maneuver with flipping sides.
Okay.
And including that maneuver and see whether it changes anything. Okay. Where we went from starboard to port side rudder and then flip back to starboard side rudder, so on and so forth. Okay, so that maneuver we can probably try to include. In fact, in that maneuver, you may not even need to decrease the rudder angle. Like, don't taper it down maybe. Go from plus 35 to minus 35, let it stabilize and move to minus 35.
Isn't that the zigzag?
No, zigzag is only in when your heading reaches a certain angle. It doesn't necessarily mean that you reach steady state R.
Okay, and in this one?
In this one,
we
we
are
are
doing steady state R. Okay.
Yeah, stabilize for R and then you make the turn.
Okay.
That is one approach. The other thing is, can we do a pure yaw maneuver?
Okay.
So that is one thing which will require some more in thought also. because now you have to deal with control, and especially with the MMG, the control will not be so easy because there are tons of coefficient in the rudder.
Yes.
Okay.
We can use an external controller, right? One that will reduce error. But we won't know the stability of it.
We won't know the stability of it. No? That's the problem.
Yeah.
Even if you say proportional, still you won't know the stability. It may blow up. Okay, that is something which you have to think about. Control. All right. Okay, sounds good. Any other questions from others? No other questions? All right. So let me stop recording now.